Thank you very much. I think we should start our today's discussion. In our last lecture, we have started discussion on artificial neural networks. And in that class, we have discussed about the basics about artificial neural network. And then if we have a data set, how to um, formulate artificial neural network from the data set. That is, how many layers we have to add, how many neurons we have to add in our input layer, and how many neurons we have to add in output layer, and how to design the hidden layer. So those things we have already discussed. And then functions of neurons and the analogy between our biological neural network and artificial neural network. And then we have started discussion on training in neural network. That means neural network training. And I have mentioned that specifically the training, it has two phases. One is called forward propagation and another one is called backward propagation. And in forward propagation, we predict the output from the input that is in forward propagation. That means it will propagate some form of computation to produce output or predicted output from the input. And we have discussed that part, that is the forward propagation part. We have considered this example. We have taken just one input, 1, 1, and the expected output is 0. But if we input this 1 onto this network, then we have predicted that the output is 0.774. Okay, so this is the output, 0.774. And the internal computation we have already discussed about the internal computation. What are the internal computation performed in each and every neurons? Okay, specifically in hidden layer and output layer. And also we have discussed, that means activation function, specifically a sigmoid function, to make the linear to nonlinear equivalent programs. Okay, and after that we have started the backpropagation. And in backpropagation, the first step is to calculate the error. Okay, that means we have to determine the error, because from our data set, this is the data set we have, and we can see for input 1 and 1, the expected output is 0. So this is just expected. But according to our design, that is current design, specifically the current weights, the value of the different weights, these are the initialized weights. Okay, so initially we assume that these are the weights. And if we consider the weights value, these are the weights value, and then feed 1, 1, that means feed the input here to this network, the output we got 0.77. But what's the expectation? Expectation is 0. So that means if we input 1 and 1, the neural network should produce the result 0. So that is called the expected result. But we got 0.77. So that means we have just trained the network in first phase or first iteration, first epoch. And that's why the result is too far from the original. The original is 0, but it returns 0.77. So we have to continue the second iteration, third iteration, fourth iteration. That means we have to continue the approach. Then for each and every approach, what it will do, it will try to reduce the error. So it will try to get the closer output of 0. So that's why it will try to minimize the error each and every time, every iteration. Then we have to determine how much error we have already in the first iteration. So in the first iteration, the error, it will be, this is the prediction, the predicted output, and this is the original output. So original minus prediction. So we can see that there is the target minus calculated value. So that original minus prediction. So original minus prediction is negative 0.77. So this is the error. So this is the error. So now we have to reduce the error. But how can we reduce that? So for that, specifically, we cannot change this input 1 and 1, because for the 1 and 1 we want to get 0 here. So that means we cannot change 1, cannot change the input 1 on 1. So what are the remaining things we can change? The remaining things are the weights. Okay. So weights are our learning parameters. So that means we can change the weights, and after changing the weights, we will get maybe 0. We have to change the weights in such a way so that we get the 0. Or in another word, we can say that we have to change the weight in such a way so the error will be minimized. Error will be minimized. So this is error. It will be minimized. So if error needs to be corrected, then we need to change what? We need to change this value. We need to change this value, that is calculated or predicted value. Then how we got that value? You can see the calculated value or predicted value. Already we can see that this is the last equation. That is calculated value we will get from the sigmoid of 135. Sigmoid of 135 is our 0.777. So that means this sigmoid value we need to change. Okay, so if we want to change this value, then we need to change this sigmoid of 1.235. Okay, sigmoid of 1.235. We need to change here. So therefore, that means if we change this one, then only from that we can change the 0.774. And if we change the 0.774 in right direction, then only the error will be minimized. Okay? Error will be minimized. So maybe in such a case, maybe if we can see that, okay, calculated value is 0.77. So if it is maybe 0.1 or maybe 10. If it is this instead of 0.77, then the error will be 0 minus 0.10. So on that case, it will be minus 0.1. So this is negative 0.77, but this is negative 0.1. So that means this is minimized, kind of. Error is reducing. Okay, this is reduced error. So therefore, we have to change our sigmoid value. Okay, change our sigmoid value. So how can we change that? So this sigmoid value, actually this sigmoid, it will also depends on what? The sigmoid of 1.235. 1.235, it comes from this equation. That means the sigmoid of H1, then W7, sigmoid of H2, then W8, and sigmoid of H3, then W9. Okay, sigmoid of H3 times W9. Then W7, W8, and W9, these values we need to update. Okay, these values we need to update. So that means the weights we need to update. So then okay, we confirm that maybe words we need to update, but how much change we need to do for each and every verse? Like for the W7, currently W7, the value of W7 is what? Currently it is 0.3. Currently W7, the value of W7 is 0.3. But how much change we need to do? W7 is 0.3, the 0.3. So whether need to add something or maybe we need to subtract something, okay? So that means whether we need to reduce the weight or we need to increase the weight. So we don't know about that. But we need to know that is whether we need to increase the weights and decrease the weights. And if we know that maybe we need to increase, then how much we need to increase? And if we know that no, we need to decrease, then how much we need to decrease? So that means these weights we need to update. And after that, after updating these weights, we will try to update these weights. Okay. So that means kind of the error is propagating back. So here at first maybe these words and then these words. Okay. So that's why usually we call it back propagation. Okay, back propagation. So now we know the error. We know the error, and the error the generated error is from the sigmoid of the sum. Then we need to think about like if we change the sum a little, then how much it will affect to our error. Okay, so we need to determine that. So it is like our graph here. You can see this is the sigmoid of the sum. Sigmoid of our sum. So this is our sigmoid of the sum. Sigmoid of the sum. Then the sigmoid of the sum, it is actually depends on, we can see that sigmoid of the sum, it depends on sum. Then the result will depend on the sigmoid of the sum. Okay. So that means how much change we need to do in summation to get a little change in results. So how we compute that? That means if we consider about any equation we have, y equal, maybe you can say, y equal 2x square plus 3x plus 5. Okay, we want to find out dy by dx. Okay, dy by dx. It means based on the change of the x, we want to know the change of y. Okay, that means for the little change of x, how much change will happen to y. So that is our dy by dx. So now we want to find out that, okay, to find out that. That means we can say sigma of the sum is a result. But if we take the derivative of our sigmoid function. So here this is sigmoid of the sum. If we take the derivative of that, so then we can find out, that means how much change of sum will change the result, and based on that it will change the error also. Okay, error also. So therefore we can see here that that is we need to take the derivative of our sigmoid function. So this is our sigmoid function. Now we need to take the derivative of our sigmoid function. So S prime sum. S prime is our derivative of our sigmoid of the sum. That is d sum by d result. Okay, d sum by d result. Now the d sum by d results, the rate of change of result based on the delta sum. Then if we multiply this one with our error, so that is target result minus predicted results. Target result minus predicted results. Then we have to take the derivative of the sigmoid of the sum with respect to result. Okay, so this is called our delta sum. Okay, delta sum. So that means rate of change of sum. Now the derivative of the sigmoid, how can we compute that? The derivative of the sigmoid is easy to compute. Okay, easy to compute. We know that sigmoid function is 1 by 1 plus e to the power minus g. So sigmoid sigmoid function, we know the sigmoid is 1 by 1 plus e to the power minus g. Okay, so this is our sigmoid function. Then if we take the derivative of the sigmoid, that means d of our sigmoid based on delta x. So we want to find out that. Finally, you will get that if we take the derivative of the sigmoid function, then it will provide us the sigmoid of the sum, then 1 minus sigmoid of the sum. Okay, so that means we can easily find out the derivative of the sigmoid of the sum. So that means we can say if we know the sigmoid of the sum, and we have already we have known that because previously when we are in forward propagation, we have already calculated the sigmoid of the sum. Here is the sigmoid of the sum. Okay, we have already calculated. So if we want to calculate the sigmoid of the derivative of the sigmoid of the sum, it will be the sigmoid of the sum times 1 minus sigmoid of the sum. Okay, so that means the sigmoid of the sum and 1 minus sigmoid of the sum. Okay, so this is our derivative. This is derivative. So it's easy because already we have computed the sigmoid of the sum, and using that sigmoid of the sum and 1 minus sigmoid of the sum, if we multiply these two, then we will get the derivative of the sigmoid of sum. Okay, from this discussion, we can see that is the delta sum. Delta sum, it is delta sum by delta results and times the error. Okay, error. So that means the delta output sum, it will be derivative of the sigmoid of the sum times output sum margin error. We know the error. We have already calculated the error. Error is negative 0.77. So we need to put that one here. So negative 0.77, we put that. And then derivative of the sigmoid of the sum. So if we want to find out the derivative of the sigmoid of the sum, then how can we find out that? So A is sigmoid of our 1.235. And then 1 minus 1 minus sigma out of the 1.235. Okay. So this is the derivative of the sigma out of the sum. And then, so derivative of sigma out of the sum, it means the sigma out of the sum. So what's the sigma out of the sum? We have already calculated. It is 0.774 or 0.775. So it will be 0.774 times 1 minus 0.774. So 0.774 times 1 minus 0.774, then times negative 0.77. Negative 0.77. Okay. So then if we do the math, we will get negative this one, that is negative 0.1343. Okay, 1343. So this is our delta output sum. Okay, delta output sum. Delta output sum is negative 0.1343. But we need to find out delta weight. That is rate of change of weights. But we already found delta output sum. Now we need to build a relationship between delta output sum and our delta weights. Delta weights means that is the rate of change of weights. Okay, so we need to know the rate of change of weights. Okay, so that means specifically we need to find out that is the delta W. So delta weights. In our case, these are the weights of our hidden layer to output layer. So we can say this one as H2O. So H2O. So that means delta WHO. So we need to find out that. Okay, delta WHO. So now one relationship we know that is the delta hidden results times hidden results times weight. It is output sum. Why this one? Previously we have already used this. The hidden results. Hidden results are the results from hidden layer. So these are our hidden results. These hidden results times the W7 plus these hidden results times the W8 plus these hidden results times the W9. So that is our output sum. Okay, that is our output sum. That is our output sum. So that's why we know this relationship. Okay, we know this relationship. In our forward propagation already we have used, that is hidden results. We have to multiply with our WHO to get the output sum. Now what we have to do, what we want to do, we want to take the derivative of this equation. Okay, derivative of this equation. So we have to take the derivative of this equation with respect to W. With respect to W. So if we take the derivative of this equation with respect to W, then W will be 1. So that means the hidden results times 1, then delta O sum by delta W. So that means in this part we will get delta O sum by delta W. And in this part we will get just only the hidden results because WHO equal 1, because we are trying to take the derivative of this equation with respect to W. Then we will get delta O sum divided by W HO equal hidden results. So it means what we want to find out, this delta WHO. So it means if we try to find out the WHO, it will be delta of sum divided by hidden results. Okay, so that means this one we have to place there. So delta of sum by hidden results. Okay, delta of sum by hidden results. So that will be our WHO. Delta hidden H2O. Okay. Now the delta output sum. We have already calculated the value of delta output. This is our delta output sum. Delta output sum. The value of the delta output sum is negative 0.134. Okay, 134. And hidden results, we have already calculated the hidden results. So that means these are the hidden results. So these are the values of hidden results. That is 0.73, 0.79, and 0.69. So those are our hidden results. So therefore, if we divide our delta output sum, so this value by our hidden results, then we will get our delta weights. So here the delta output sum divided by delta hidden results. The delta output sum is negative 0.134. So that means this one. And we have to divide it by the hidden results. So 0.73, 0.79. So here is 0.73, 0.79, and 0.69. So that means on that case, it will be 0. This one divided by that value, and the same this one divided by that value. And then we will get the delta words. So delta words, it will be negative 0.18. Then this is negative 0.17, and this is negative 0.19. So those are our hidden, that is delta words. That means rate of change of the words. So now, so these are our old words. So these are our old words. Okay. So we know the value of the delta words. Then we need to change it. So new words will be the old words plus of delta words. Sometimes we also do this, that is delta words times the learning rate. LR. Okay, so we have considered this one, or learning rate is 1. This is impractical. Practically, learning rate will be maybe 0.0001 or 0.001 or at least 0.01. So the old words. Now, let's say that is we want to find out the new weight of W7. So it will be old words. So old words is 0.3, 0.3, and then delta words of W7. So the delta words of the W7 is this one, negative 0.18. Okay. So negative 0.18. So now we can see it is 0.3 plus negative 0.18. Okay, we have considered the learning rate is 1. So it will be 0.73 minus 18. Okay, 0.3 minus 18. So here it will be 0.12. Okay, 0.12. So here it is W7 new versus 0.1162. So 1162 is equivalent to 0.12. Okay, 0.12. So this is how we have to calculate also W7, so W8 and W9 using this equation. So these are our new words. Okay, these are our new words. So that means these words we have updated. But now what we have to do, we have to think about updating these words. Okay, updating these words. So that means these words are actually our W, the input to hidden layer words. So again, we need to find out the delta of this. So delta W is, because how much change we need to make here in these words. So W input to hidden layer words. Okay, so again, at first we need to derive the equation and then we have to apply those equations to find out the updated words. To derive the equation, again, we want to use the equations we have used in our forward propagation. So that is hidden results WHO equal O sum. So this equation, again this equation, previously we have discussed this equation also here. So this one, that the output sum, it will depend on hidden results and WHO. So in this case, so here, hidden results times WHO equal output sum. Now, previously we have derived this equation. We have take the derivative of this equation with respect to W. But this time, instead of taking the derivative with respect to W, we want to take the derivative of this equation uh, with respect to with respect to um, with respect to what? So with respect to delta, with respect to O sum. Okay, so that means we want to take the derivative of this equation with respect to O sum. Okay. So if we take the derivative with respect to O sum, then it will be delta hidden results. So it will be delta hidden results and then delta O sum and then WHO equal, here is this W O sum, okay, O sum. So we are taking the derivative with respect to O sum. So what we will get? We will get 1 on this side, in the right hand side. Okay, in the right hand side we will get 1. It means we will get delta hidden results by delta O sum. So delta hidden results by delta O sum equal 1 by WH. So 1 by WH. Okay, so we will get this. Now from this equation, if we want to find out delta hidden results, we have to multiply both of the side by delta O sum. Okay, so delta O sum. Then both of the side we have to multiply with delta O sum. Okay, delta O sum. And now we can see that is so in this part we will get what? We will get only delta hidden results. So here is the delta hidden results. And in right hand side we will get delta O sum by WHO. Okay, delta O sum by WHO. So delta O sum, that means delta hidden results equal delta O sum by WHO. Now, what we want to do, let's say this is equation number 1. Okay, equation number 1. And now we know that these hidden results, that is these hidden delta hidden results, these hidden results, those are also generated from our sigmoid function. Okay, sigmoid function. In our forward propagation, we can see there is the sigmoid of H1. This is sigmoid of H2. So sigmoid of H1 is hidden results of hidden neuron 1, and the hidden results of hidden neuron 2, hidden results of hidden neuron 3. We have computed those values by applying the um, hidden layer values, the sigmoid function on our hidden layer values. Okay, so that's why we want to apply the same thing here. So that means the derivative of the sigmoid of hidden sum, it will be delta hidden sum by delta hidden results. Okay, delta hidden sum by delta hidden results. Because previously we can see there is, if we can remember this equation, this is sigmoid of the sum is results. Okay, there is sigmoid of the sum. This sigmoid of the sum is result. So this equation is also value that means valid for sigmoid of our hidden sum. Okay, hidden sum equal hidden results. So then what we can do, we can find out the derivative of the sigmoid of the hidden sum. So derivative of the sigmoid of the hidden sum will be like here. Derivative of the sigmoid of the sum is delta sum by delta results. Then derivative of the sigmoid of the hidden sum, it will be delta hidden sum by delta hidden results. Just we can say, instead of sum, we have to think about the hidden sum, H sum. Then it will be delta hidden sum by delta hidden results. Okay, same equation. So this equation we want to apply here. So this is the case. So that means derivative of the sigmoid of hidden sum, it will be delta hidden sum by delta hidden results. Okay. Now, what we have to do, delta hidden sum by delta hidden results, this one, we have to multiply the both side of equation 1, both side of equation 1 by this one, that is delta hidden sum by delta hidden results. So that means this side we have to multiply with is a delta hidden sum. So delta hidden sum by delta hidden results. This side also, there is delta hidden sum by delta hidden results. So both sides. If we just multiply the both side of equation 1 by delta hidden sum by delta hidden results, then we can see this is delta hidden results and this is also delta hidden results. Okay, so we can cancel these two out and then we will get delta hidden sum. Okay, so that is delta hidden sum equal, we will get delta O sum by WHO and delta hidden sum by delta hidden results. The delta hidden sum by delta hidden results is what? It is derivative of the sigmoid of sum. So that's why it is derivative of the sigmoid of the sum. And this side we have only delta hidden results. Sorry, delta hidden sum. So here the delta hidden sum equal delta output sum by WHO times derivative of sigmoid of hidden sum. Okay, this equation. So now we know that delta hidden sum, the value of delta hidden sum also, and we know the WHO, that is the W, these are our WHO, hidden to output layer, these values. Okay, and then we have the sigmoid of the hidden sum. So we can easily derive the sigmoid of the hidden sum because previously in our forward propagation we have already calculated those values of sigmoid of the hidden sum. So derivative of the sigmoid of the hidden sum, it will be the sigmoid of the hidden sum like sigmoid of the h1 times 1 minus sigmoid of the h1. Similarly, sigmoid of the h2 times 1 minus sigmoid of the h2. Okay, so this is how we can compute our derivative of the sigmoid of the hidden sum. Okay, so now we can see if we put those values in our equation. So in our equation is delta hidden sum, delta output sum divided by hidden to output weights times sigmoid of hidden sum. Okay, so we know that delta output sum, the value is negative 0.1344. So previously we have computed this value. So this is the delta output sum. Okay, so negative 0.134. So that value is this divided by hidden to output layer weights. So we know the hidden to output layer. These are the weights: 0.3, 0.5, and 0.9. So here is the 0.3, 0.5, and 0.9. And times derivative of sigmoid of hidden sum. So derivative of the sigmoid of our sum is 1, 1.3, and 0.8. So for that 1, 1.3, and 0.8, we have already calculated the value of sigmoid of 1, and then sigmoid of 1.3, and sigmoid of 0.8. Like the sigmoid of 1, we have computed the value is 0.73. Okay, so sigmoid of 1, previously we have calculated in our forward propagation that this is 0.73 something. Okay, 73. Then if we compute the derivative of the sigmoid of 1, it will be 0.73 times 1 minus 0.73. Okay, 1 minus 0.73. So this will be our derivative of sigmoid of 1. Okay, derivative of the sigmoid of 1. Now we can see it will be 0.1966. We have already computed that. If we do the math, derivative of the sigmoid of 1, it will be 0.1966, and derivative of the sigmoid of 1.3, it will be 0.1683, and derivative of the sigmoid of 0.8, it will be 0.2139. And this part, that means this part, from this part we will get negative 0.134 divided by 0.3, you will get this value, and negative 0.134 divided by 0.5, you will get this value, and 0.1344 divided by 9, it will be 0.4493. Now you can see we can just multiply these two. So if we multiply these two, that means this value with that value, and this value with that value, and this value with that value. Okay, so we will get the delta hidden sum. Here is the delta hidden sum. So these are the values of delta hidden sum. So after computation of the delta hidden sum, okay, we got the delta hidden sum, but what we need to find out these values, that is delta weights, delta W input to hidden unit. So we want to find out that, but we get already delta hidden sum. Okay, so that means delta is sum. delta hidden sum. Okay, delta hidden sum. So now to get the delta wi, we need to do a little more math. So another equation we have already utilized. That equation is input value times wi equal hidden sum. So that is in our forward propagation. We have already utilized that equation. So that is these are the input values, and then w we got the age hidden. So that means input value times w. So we have already utilized this equation in our forward propagation. Now we have to take that. So input and ih. So that means weight of input to hidden layer. So that means these are the weights for that. If we multiply these two, then we will get the hidden layer values, not the hidden layer result. That is 1.3 and 0.8. Okay, 1.3 and 0.8. So those are our hidden sum. Now, utilizing this equation, we want to take the derivative of this equation with respect to WIH. So that means with respect to WIH. So if we take the derivative of this equation with respect to WIH, then in left hand side, what we will get? In left hand side, we will get just only I, because we have already taking the derivative with respect to W. So it will be I equal delta hidden sum by delta W HO. Okay. So from this equation, what we want to find out? We want to find out the delta WHO, this one. So if we want to find out delta WIH, so not the HO, it is IH, it will be delta hidden sum by I. Okay. So delta hidden sum by I. From this equation, we can get it is delta WIH, it is delta H sum by I. So now we already calculated delta hidden sum. So these are the delta hidden sum, the values of delta hidden sum. And we know that the I is our input. We have considered the input as 1 and 1. Okay, so now just put the values here. So delta weights equal delta hidden sum by input data. So the delta weights already we have calculated. These are the delta hidden sum, and input weights at 1, 1. So now divide. So that means we will get, this is 1. So that means we will get these three values. And again, we have to divide by 1. So you will get again these values. So these are our delta weights. Okay, delta weights. Now we already got the delta weights. So we can now update our weights utilizing this equation. Okay. So previous weights, then plus of delta weights. We'll get the new weights. So here we can see these are our previous weights. That means these weights. Then utilize this equation. So utilize the delta weights values. So these values. Then we will get, these are our updated weights. Okay. So these are our updated weights. Instead of these weights, in our next iteration, we will use these weights. So now we have previously calculated the updated weights of this layer. And now we have calculated the updated weights of this layer. So if we do that, so in our second iteration, okay, so these are the updated weights, utilizing the updated weights. Again, if we perform the forward propagation using these updated weights, then maybe we will get different output. So now we can see the different output here is 0.69. So 0.69. Previously it was 0.774. the output. Now it is 0.69. So 0.774, it is far from the 0, but 0.69, it is better than the previous value. Okay, so because this is also more closer to 0. Okay, so that means if we compute the error, then it will be less error. So it is the second iteration. Okay, second iteration, and again we have to perform the back propagation to update the weights of hidden to update the weights of our hidden to output layer, and then out input to hidden layer. And maybe after many iterations, you will get the expected output 0. So this is how our back propagation in artificial neural network worked. Okay, I think we have to stop here. So in our next class, we will continue the discussion on neural network. Okay, neural network discussion, because we have to discuss the bias, and also we have to discuss the step-by-step solution for our best processing. That means we have to consider the input base instead of considering maybe just only one input. Okay. So in our next lecture, we will discuss it. Thanks everyone for joining this session. Do you have any question or queries?
No, sir.
Okay. Okay. Thank you. Thank you for joining. See you in our next class.
Assalamu alaikum.
Alaikum salam.
Assalamu alaikum.
Alaikum salam.
Sir, assalamu alaikum.
Alaikum salam.
Sir, assalamu alaikum.
Alaikum salam.
স্যার আজকে প্রেজেন্ট নেবেন না?
না, আজকে সবাইকে অ্যাটেন্ডেন্স দিয়ে দিব, টাইম কম তো ওই জন্য নিলাম।
ঠিক আছে, আসসালামু আলাইকুম স্যার।
ওয়ালাইকুম আসসালাম।